Okay, I guess we can start. So, as I had mentioned before, we have basically covered most of the topics I wanted to discuss. So, if everything goes according to plan, today will be the last day where I kind of give you new material for the final. So the final will be 1 week from today. Essentially will be basically with the same format as the one we have been doing. It's just that it will have like an extra part. So instead of being 2 parts to the exam, it will be 3 parts. So I think guys will do it from 1 to 4, um, if that's okay. But everything else is kind of like will be structured the same. So what I want to do, yeah, it's kind of finish today the material for the exam, and then it is cumulative. So basically, but my idea is kind of like do half of the problems about like the new stuff that we have been discussing after midterm 3, and the other half based on problems from before. So you could still see like a problem from the first midterm or a problem from the second midterm, problem from the third midterm on the final. But I will try to do it like half and half. So um, but yeah, what I want to do is kind of like finish today most of the stuff so that I can then give you over the weekend like some other practice problems and things like that for the final exam. And then if that goes if it goes according to plan, like what we would do on Monday, Tuesday, and Wednesday, it's kind of more like flip the lecture. So it's really you would come like we would just go over any problems that you want me to go over, like kind of discuss like practice from my lab or like anything else I have posted, um, things of that sort. So it would be more like for practice stuff. Um, so yeah, that's kind of what I was planning on doing. I'll also try to finish creating all the quizzes by over the weekend so that you have feedback on that as well. So is that okay? Is that making sense? Okay, so again, like today's kind of like more like random topics that I haven't mentioned before. So I wanted to start with kind of like a list of things because like again like we kind of already went through like, all the major techniques that you need to know. So here like some things that are we haven't discussed first. So we had so topic 1 is this relation between position and velocity. So if you remember, I may have mentioned this a couple of times uh, a while ago. If like say if you have like a car, so here's a car. Well, not the best picture again, but so here's a car, and then you can think of the position of a car as a function of time, right? So the first thing you can do, I mean, we have seen that the velocity of the car, right, will be the derivative of the position with respect to time. Right? So v of t, which is the velocity of the car, is dx dt, right? So in most of the problems, we didn't do that many problems with velocity, but in the problems that we had done before, like I would give you like the position as a function of time, and then I would ask you to find the velocity, and that's kind of easy to do because that just requires taking the derivative. But now that we have studied integrals, we can actually do the reverse. So now we can do the reverse problem. So by that I mean that, namely, if I gave you the velocity as a function of time, right? How can we find the position vector? Now we want to find the position vector. Sorry, I'm saying vector because I'm thinking about the other classes I'm teaching. How do you find the position function? Okay. So again, to go from position to velocity, you take a derivative. So now how could you go from velocity to position? It's going backwards, right? So it's kind of undoing the effect of the derivative, right? So what should that be? What do you think it could be? Like it's an integral, right? Like, so you should think of this antiderivative or the integral as kind of undoing the effect of um of the derivative. So what, like, the idea is to take the integral of the integrate the velocity to find the antiderivative for the velocity. So the idea is to find an antiderivative or the velocity function. And that will give you the position basically. Mm. So let's do some examples. What's nice here is that you'll finally see why this constant that we have been using writing every single time is useful, because like up to now it may look like a waste of time because it kind of always went away when we were when we were evaluating a definite integral. But for these problems, it's kind of useful to have it around. So you'll see. So let me make a concrete problem here. Sorry for my pictures. Uh, let's say that here you are, and you were ordering a car, but the car forgot an Uber, but they forgot about you, so they just kept driving. Uh, so let's say that you know that the velocity of the car as a function of t of t equals e to the negative t. Okay, let's do that one. That's nice. Okay, and you'll see that's going to be enough to find the position. But if you actually want to get rid of the constant, when we write the antiderivative, we need something else, which is called the initial position. So you have to also specify how far the car was away from you when you started measuring time, for example. So let's say the velocity of the car is e to the negative t, and the initial position of the car from you is, let's say, it was, I don't know, 2 miles. Okay. So, I mean, this, you could think the velocity here is like what? Miles per hour. It is going to be fine. Okay, yeah. So, a question you could ask is just to find the position as a function of time. So here's the problem. Find the position as a function of time. Okay. So what we should do is like, yeah, we should integrate the position. Sorry, we should integrate the velocity because like the position is like an antiderivative for the velocity. So now the question is, how do you integrate e to the negative t dt? Anyone knows that? How could you do this? What's the antiderivative for e to the negative t? What could you do? Excellent. Yes. So let's do, in case it's not so clear, let's do like a substitution. So like the substitution is going to be negative t. So if you do the substitution, again, after a while, you may memorize this already, so you don't have to think up in so complicated ways about this. But if you do that, then you can say that du is minus dt. So minus du equals dt, right? So what happens when you do that u stop? This becomes e to the minus t, which is e to the u, and then dt is minus du. So this is minus like the integral of e to the u du, but e to the u, like the integral, like the exponential function is just an exponential function. And again, the constant of integration, you can put it somewhere wherever you want. So you get minus e to the minus t plus c. Is that okay? So what this is saying is that the position as a function of time minus e to the negative t plus c. Is that making sense? Again, I'm not saying that you always, like for something like this, you can kind of guess the answer for the antiderivative, but if you want, you can always do it like carefully with the substitution, which is what I just did. And so that gives you the position of the car as a function of time. Okay. Now the thing is that here you see there's this constant which we haven't resolved. We haven't, like, it's not useful in this problem to have a constant because like then we don't really know the value of the position unless we know the value of this constant. So to find the value of t, that's where we have to use the other piece of information that at time 0, the car was 2 miles away from you. So to find the value of C, we must use let's see, x of 0 equals 2 miles. So that means that the position at time 0 must be equal to 2. So how can you, what is that, what does that mean? What if you plug in t equals 0 here? So that means that 2 miles has to be the same as minus e to the minus t plus c at t equals 0. Yeah, you can forget the units if you want. Otherwise you get confused at this point. So this, because this is like the formula for the position at any time. So if you plug in t equals 0, you should get 2. That's the idea. And so you get 2 equal, what is, you get minus e to the 0, no, you get minus e to the minus 0 plus c, right? But what is e to the 0? E to the 0 is 1, right? So you get 2 equals minus 1 plus c. So c is actually 3, right? So that means that the position function that we were after is really x of t minus e to the minus t plus 3. Is that making sense? Uh, and now, I mean, if you want it, like in this case, you could also write it, I mean, this, you can also write it as x of t equals minus 1 over e to the t plus 3. Right, so, or even like, you can put it like 3 minus. It's nicer to write it that way. So, this is giving you, this is giving you the position as a function of time. So you can ask now, okay, I can like, the car is driving away from you, right? So then you can ask, how far away will it get from you, right? Or if you prefer, like how, like, you know, if you let, if after 1 hour, after 2 hours, after 3 hours, after 4 hours, like where is it going to be located? So you can ask like long term, where is the car going to be located? And sometimes the way you say that is like, what's the position at t as t goes to infinity? So that's kind of like saying very, very into the future, you know, if you wait hours or days or months, whatever you wanted to wait, like where is the car going to be? So what's the limit as t goes to infinity of x of t? What's the limit in this case? That's the limit as t goes to infinity of 3 minus 1 to the e to 3 minus 1 over e to the t, and that's what? Um, what is the limit? The thing is like as t goes to infinity, right? The exponential gets really, really big, right? As t goes to infinity, the exponential is really, really big. So, so what does that mean? It means that, you know, this fraction is becoming like very close to zero, right? So since this fraction is getting closer and closer to zero, the limit should just be 3. Um, Another way to do it, if you don't like doing it this way, is that you can do L'Hopital. It's a little bit of an overkill, but you know, that's okay. If you rewrite the fraction this way, then this is like kind of infinity over infinity. So you can do L'Hopital's theorem here. And if you do L'Hopital, you're taking the derivatives of each, the numerator and the denominator. But the derivative of the numerator is 3 e to the t, and the derivative of the denominator is e to the t. So the e to the t's cancel, and you just get 3. Is that making sense? So again, like you can do it either way. There are a couple of ways to find this limit, but what this is saying is that if you just wait and wait and wait and wait and wait for an eternity, at the end of that eternity, the car will be 3 miles away from you. So it didn't move that much. Is that making sense? And then this is also you can do like a similar idea for like these problems which are called population growth problems, or like radioactive decay problems. So like so in this case, in these types of problems, you have like a stuff, like for example, in the radioactive decay substance, you have like a radioactive substance, could be uranium or plutonium or one of those, whatever. And so imagine that it's like in some sort of container. So you have some radioactive substance. And you can call n of t the amount of the substance that you have at time t. So this could be measured like in grams, like probably you don't want to, or kilograms, or like some unit, like usually having a little bit of radioactive material is already dangerous enough. So you don't want to have that much. So you could say, but the point is that these obey like an equation. Like the way to model how this changes over time is that these obey the equation. This function obeys an equation like um, So this is saying that where k is a constant. So what this is saying is the how fast the amount of radioactive substance you have is proportional to how much substance you have left at that time. The same happens in the most simple models of population growth, like in biology or bacteria, which is like how many more, like say how many individuals are being added to the population, kind of depends on what's the number of individuals you have at that time. Or if for something like for bacteria, which reproduces really quickly, that kind of makes sense. It's a good approximation. You see that, so like it's saying just like the amount of bacteria that are, the new bacteria that you're getting at time t is proportional to the amount that you have at that time. I mean, in reality, there's always some delay because it's not that they reproduce instantaneously, but for certain purposes, that's kind of good enough because they do reproduce pretty quickly. You see? So for example, let's try to solve like we can solve this in exactly the same way as what we were doing here. So here's an example. Suppose that the amount of uranium you have at time t obeys the equation and that initially n of 0 equals 4 grams of uranium. Okay, so the problem could be like a typical problem could be like find the amount of uranium. Sorry, find n of t. So how much uranium you have at time t. And in these radioactive decay problems, or like again many problems involving exponential growth or decay, you can also ask for the half-life. So find the half-life. That is at what time you have half the amount you started with. That is at what time you have 2 grams left. Okay. So that's half of the initial amount you started with. And that's actually, this half-life is useful to kind of, when people check for the ages, like, of like, when they look, do like an archaeological excavation of like, of an ancient civilization or whatever, and they have artifacts from them that they recover. Sometimes they want to know, well, what are these artifacts from 10,000 years ago or 20,000 years ago or so on. And one of the ways that gets done is like by analyzing like a similar problem of this sort where like you kind of, I think you count like some sort of like radioactive material in the sample, you measure it and you estimate that half, from how long ago the material the object could have been constructed. So I'm just saying it is kind of like a problem that's not completely artificial, although we're doing like a very simple model for it. Okay. So the idea for these problems is that I don't know if eventually some of you will take this course called differential equations, which is what math 244. If you take differential equations, you will do things like this all the time. So differential equations is kind of like doing this over and over and over in more sophisticated ways. Um, and you'll see in that course that basically what you need to do is integrate, 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 integrate. So you just integrate forever. Um, so like the idea here is that you kind of like want to integrate this equation, but you kind of move everything with everything you kind of separate the equation according to the variable. So everything that has a variable n goes to one side, and the stuff with t goes to the other side. So like the way to do that is you can rewrite this as dn over n equals minus d, oh sorry, minus 2 dt. Okay. So now everything has n on this side, and everything has t on this side, or has the other variable. In this case, t is not explicitly there, but I just mean like there's a dt here. And then what you do is kind of like integrate both sides. So what you would write is something like this. So it's kind of similar if you remember, like when we were doing implicit differentiation. When we did implicit differentiation, we would have an equation and we would take the derivative on both sides of the equation. This is kind of similar where like we're kind of integrating both sides of the equation, or we're finding the antiderivative for both sides of the equation. Okay. So once you get to this point, every side kind of gets analyzed on its own. So here, what would be like what's an antiderivative, or what's the integral of dn over n? It looks a little bit weird because maybe I'm using a different letter, but it is one that we have seen before. What do you think this should be? Excellent. Yeah, the thing is like this is a kind of dx over x. It's just like an illusion because we're using different like letters, you see, but it is really the same logic, but with a different letter. So it has to be natural log of n. I mean, the population is always going to be positive because it's like like the mass is positive. So I'll take the absolute values in a second, but and then what would be the integral of minus 2 dt? Anyone knows? It's just remember when there's a constant, it's only like that constant times a variable, so it's minus 2t, right? Because the derivative of this with respect to t is just minus 2. And then there's a constant of integration. Like in principle, there's like a constant of integration or a constant for each of these. But again, you can always recombine them if you want into a single quantity, into a single constant. So there's really no need to put two constants, one for each here. At the end, like the important thing is just to have like a constant that represents all the possible constants you could have written. So you could have had like C1 and C2, but then you can move them together and call that C, and that's all that really matters. And then how do you solve this equation for C, for the N? Well, you can exponentiate both sides. Is that making sense? So that gives you the amount of uranium at time t. This gives you the amount of uranium at time t. It's kind of still incomplete because I want to use the fact that I still have this that depends on this constant. I don't want to have the constant. So I have to use the fact that at time zero, right? At time zero, we had 4 grams. So at time zero, we had 4. So that means that 4 should be equal to e to the minus 2 times 0, right? Times e to the c, right? So 4 equals, what is e to the 0? E to the negative 0, that's just 1. So 1 times e to the c, so that means that e to the c equals 4, right? And that's all that you need. I mean, you could solve this for c by taking natural log, but that's not important because that's what appears in the, e to the c is what appears in the formula. So that means that the population as a function of time is really 4 times e to the minus 2t. And this is the answer we want. This is the correct formula. Is that making sense? So that's the formula for the decay for how much quantity of radioactive quantity of the substance you have at time t. Now, for the second part, we wanted to find the half-life, which just means like when is it when at what time do we have 4 grams, right? So at what time do we have 4 grams? Sorry, 2 grams, because that's half the initial amount. So what is that time? Well, you would have, you want this to be 2, right? You want this to be 2, so you want 2 to be 4 times e to the minus 2t, right? So what is that? That is 1/2 equals e to the negative 2t. And how do you find t from this equation? You can take ln on both sides of the equation, right? Oh, sorry, this gives you minus 2t, right? So t is, I mean, if you wanted, not that you need to, but you can write this as ln of 1 minus ln of 2 equals minus 2t. But what is ln of 1? Do you remember that? Ln of 1 is just 0. So you get minus ln of 2 equals minus 2t. I guess it's more elegant to write it this way. So t is ln of 2 over 2, right? So this is the half-life. Is that making sense? Okay, now okay. What? Here's another question. What? Let me see if you know what the answer is. At what time do we have half of the half-life? Do we have half of the half-life of the sorry? At what time do we have 1 gram? Right. Which is half of half, right? Half of half. So half of half the emission amount. So I started with 4. We already have the time that we get to 2 grams. Now I want the time that we get to 1 gram, right? So what's that time? Can anyone tell me? We can also solve it again, but like, what is the answer here now? Good. But what is ln of 4? 4 is 4 squared, right? Sorry, 4 is 2 squared. So you can pull out the 2, right? So it's ln of 2. Is that making sense? And what is ln of 2? It's twice the half-life, right? So this is twice the half-life. So that's why the half-life is a useful concept, because if you have the amount that you have, that you started with, and you have it again, it just takes you like twice the half-life. And you see what I'm saying? So for example, I started with 4, I went to 2, now I'm going to 1. What's half of 1 is 0.5, right? So if I wanted to know how much time it takes me to go to 0.5, I just multiply this by 2 again. So I get 2 ln of 2, you see? So it's kind of like, it's always differs by multiples of 2, the answers, like with respect to the other one. So what I'm saying is like, if I had like 4 grams, if I had 4 grams to 2, this takes me ln of 2 over 2 amount of time to get to 1. It takes me ln of 2 to get to 0.5. Takes me 2 ln of 2 times. So you see, like you keep multiplying by 2 to get to 0.25. It takes you 4 ln of 2. So it's always like different by multiples of 2. So here, like, here you shrink by a factor of 1/2, and here you multiply by a factor of 2. So they're kind of going opposites of one another. Is that making sense? So that's why the half-life is a useful, I mean, it is a useful time to find because once you have it, like it's very easy from there to get to other values for the amount of substance that you have. That's what happens usually. That's one of the properties of the exponential that makes it useful. Is that making sense? Okay. And so that's why in these population growth models, like with bacteria, it's kind of the same principle, that they can, like you could present, but it kind of goes the opposite way where like it is about growth, not decay. So it's kind of like you could find like the amount of time that it takes you to double the population. And then to double again, it would just be that amount again, like you multiply it by 2. And then to quadruple, you just multiply it by 2 again. So it kind of goes just quickly, very quickly, can like grow in size. So, uh, so or well, I guess, sorry, I meant like it's kind of the opposite. So if you double the population, like it just takes you half of that amount, and then double it again, it takes you half of that. So it just gives, it's not right, because they go backwards. So when it's like having decreasing the substance by a half, the time increases by 2, by factors of 2. But if you have like a situation where the substance is doubling in size, then the time that it takes to double shrinks by a factor of 2. So they always kind of balance each other out. So in this population growth, it just means that it keeps taking you less and less time for the population to double, you see? And that's why they cannot be realistic for all the time, because then you would have a huge number very quickly. So at some point, the model collapses and it stops working. But yeah, that's kind of how it goes. Okay, now, so these were like two, again, as I said, to them, just telling you some random topics that I had not mentioned before. Um, we're not learning any new techniques. Like the other thing that is kind of nice to know is like this formula for, this is topic 3 or topic, it's just it's the area between curves, which again is kind of like a formula that's pretty reasonable. So the idea is like if you had like a function like this, and another function like this, say from A to B, uh, then the net area, I mean, if you wanted like, okay, so if you wanted net area between the curves, you basically just consider their difference. So the net area between the curves is just the integral from a to b of f of x minus g of x. Because if you remember, like the integral was the area between the curve and the x-axis. So it's kind of like a generalization of that idea. So it's just that if you use it in this case, in this formula, you know, there will be cases where the function f is above the function g. When the function f is above the function g, this difference is positive, so this would count as positive area. And when the function g is above the function f, then this one would count, then this difference becomes negative, and so it would count as negative area. So it's kind of like the same idea that we had before between the function and the x-axis, but it's now just between the graphs of two functions. So it's nothing like, there's nothing new, like you find the areas in the same way, I mean, the integrals in the same way as before. It's just like a slightly different interpretation of it. Okay, so I can do an example to show you what I mean. So for example, here's an example. Let's see, which one can I give you? Okay, let's do sine and cosine. So I can give you sine and cosine. So here's like cosine of x. Something like that, and sine of x is something like this. Okay, I'm doing this a little bit weirdly. So I mean, it kind of looks, I'm doing this graph in a slightly odd way. So, I mean, I just care about it like in the first region. I can show you on GeoGebra because I do want that. Let's see. Let me fix it. So the one that I want is cosine of x. So this one is fine. Is there? Yeah, I just did it in a slightly odd way. And then sine of x, which is there. It's just that I called this in green. So one thing that you could ask for is the area between sine and cosine. I don't know, from 0 to pi over 4. So that's kind of what I was trying to draw on the tablet. So it's kind of, I'm going to look for this piece of area. So they intersect when x equals pi over 4, because that's when sine and cosine become the same. So what I'm asking is for like the area between cosine of x and sine of x is from 0 to pi over 4 is the integral from 0 to pi over 4 of cosine of x minus sine of x dx. I mean, each of them is easy to individually do. So the integral of cosine is minus sine of x, and the integral of sine is the integral of minus sine. I'm sorry, the integral of cosine is sine of x, right? And the integral of minus sine is cosine of x, actually. Right, because if you take the derivative of this, you get sine minus cosine, so this is fine. Plus a constant, right, let's put plus a constant. So if you evaluate it at pi over 4, you get sine of pi over 4 plus cosine of pi over 4 plus a constant minus sine of 0 plus cosine of 0 plus a constant. So sine of pi over 4 is root of 2 over 2 plus root of 2 over 2 plus a constant. Well, the constants go away as always because it's a definite integral. So you get minus sine of 0 is 0, so cosine of 0 is 1, so you get minus 1. And so you get root of 2 minus 1. Okay, so I mean, this particular one is not like, this not such a big thing because I'm not going to emphasize too much this formula about finding the area between curves because it's really no different from um from finding like the regular integral. So we don't gain too much by doing this one, but just kind of useful to know that it's there. Okay. Is that making sense? Now basically I did already said everything that I wanted to say. There's just somewhat silly thing that I should still mention. But it's very simple. So let's just take a 5-minute break. I'll tell you what that is, and then we'll do the quiz. Yeah, it's almost nothing is left. It's more like a notation thing, but it's kind of still useful to see. So I'll say like in 5 minutes. So let's just take a quick break. Okay, so yeah, as I was saying, like I already more or less said everything that I wanted to say. But I'm just going to briefly mention two things for you to know that they are there, but we're really not going to use them for anything too practical, so I'll just mention them quickly. But they're still kind of like some useful. It's good to know that they exist. So here are like some two useful. So here's like a useful convention, or let me call it convention. So in all the integrals that I have been writing thus far, whenever like I wrote a definite integral, right? Um, up to now, when writing an integral, A has been smaller than B. So for example, like if I gave you like the integral from 0 to 1 of x dx, that's just 1/2, right? Uh, but it's just convenient sometimes to have like a situation which we won't use, but it's kind of useful to have a convention for what happens if the lower bound is smaller. Sorry, if the lower bound is larger, but it is useful to have a convention for the case that A is bigger than B. So for example, what I'm trying to say is that again, I'm not going to really use this because we don't have much purpose for this, but you could have something like the integral from 1 to 0 of x dx, and just the way to deal with it is kind of like that's just minus the integral from 0 to 1 of x dx. Okay, so it's just minus 1/2. So again, it's kind of like okay, but it's not like a big thing to have. So what I'm saying is that in a sense, like in general, if you have like an integral, you can flip the bounds, but the price for flipping the bounds is just like putting like a minus sign in front of everything. Again, it's not like a thing that we'll ever use. So I don't want to like, emphasize it too much, but I'm just saying like it is like just to play with the properties. It's like a useful thing to have. That making sense? The thing is like this kind of looks odd, so it's not like a good, like, you never want to, it's always preferable to have like the smaller number at the bottom. And that's kind of how we thought about them. But I'm just saying, if for some reason, like if this came across, that's how you would deal with it. You just flip the bounds and put like a minus sign in front of everything. So again, it's not something for you to worry about, but it's kind of there. So I just felt like a little bit of responsibility to at least tell you about it, about this thing. And the other thing, which again, we're not really going to use too much, but I just figured at least I should mention it because you'll see it very often. If I don't know how many of you are planning on taking Calc 2 in the fall, it's this sigma notation for the sum. So it's just that sometimes when you write a sum, it's kind of annoying to write dot dot dot. So for example, I could write something like 1 plus 2 plus 3 plus 4 plus 5, right? I mean, that's fine. It's just like it takes a lot of space to write the sum explicitly of the first 5 numbers, five integers. And like the sigma notation for sums is just like a very elegant way of writing that same thing out. So in the again, which we're not really using for this class, but it's mentioned briefly in the book, so I figure I should tell you about it. So in this notation, like it just looks a lot more elegant because it is saying like this sigma, I mean, again, it's kind of the same letter that you see in the fraternities. This sigma means sum. And so this means start with I equals 1. Start with I equals 1. Put an I here, put a 1, and then increase I by an amount of 1 until you get to 5. So you get 1 plus 2 plus 3 plus 4 plus 5. You stop at 5 because that's so this is where you begin, and this is where you end. Okay. So it's just like a nice way of specifying like a sum without having to write every single term explicitly. Is that making sense? Um, Like for example, what would this mean? Here's another example. What would this mean? This means start with 2 and square that number. So it's 2 squared, then change I to 3 because you have to increase the value of I by 1. So change I to 3 and square that number. Then change I to 4 because we are doing increments of 1 and square that number. Then this 5 squared and you stop at 6 squared because that's the last value. So it's like it is 4 plus 9 plus 16 plus 25 plus 36. And that is whatever it is. I'm not sure what that, I mean, I guess we could compute it, but it is some number. So I'm just saying like like, you know, it's kind of like, this is saying like you're adding the squares of the integers 2 up to 6, but it's like a very convenient way of writing that out. Or another one is like you know, you could like you have like sometimes you do have to be careful because this could be, you could have something like this. So here you have to be careful because like it is like I plus 1. So there's like a plus 1 that is applied to every term of the formula. So this means like take the value of I equals 1 and add 1 to it. Then take the value of I equals 2 and add 1 to it. And then take the value of I equals 3 and then add 1 to it. Is that making sense? So that's why this would give you 2 plus 3 plus 4, which is 9. So it's like here it's just like when you see this notation, you have to be careful because this plus 1 is being added to the formula that depends on I. So that's like every term in the formula is being added. 1 is being added to every term of the formula. Is that making sense? Um, Yeah, like so. I mean, like the reason why the segment notation was useful, so that we didn't spend too much time on it because in practice, we don't need it for calculations. It's just that for the sum, for defining the sum as the limit, this is very convenient. So this is like just like a very convenient notation. This is a convenient notation for writing. Sorry, for writing like an integral in terms of the sum. Because the idea was like that when you have like a definite integral, you see, oops. Maybe you have here A, here you have B. Oops. You see, you could divide, you could have like here, like x1, x2, x3, x4, right? Because I have like 4 rectangles. So here I'm dividing like the interval B minus A into 4 pieces, right? But in general, when I divide the interval B minus A into n pieces, right? When I divide it into n pieces, each interval has length delta x equals b minus a over n. So if you wanted to approximate that's the value of the integral with the sum, what you would do is a kind of f of x1 times delta x plus f of x2 times delta x, right? Plus, remember, like you're approximating this by the area of rectangles times delta x plus f of x2 times delta x plus f of xn times delta x. It's just that that's very tedious to write, so you can just write that as in the sigma notation as, and that's what you would see in the book if you have been reading the book. You will write something like f of xi times delta x, which is way easier to write, a lot more elegant. So this is kind of like height times width, but the width in this case is kind of constant, so you could write this as b minus a over n times the sum of I equals 1 to n. I mean, well, I will write it inside so that it's not too much of a confusion. And then you would say that the definite integral was this limit. So the integral from a to b of f of x dx would be the limit as n goes to infinity of this sum. Okay, but again, like I'm not saying that we're going to use this like for anything. I just wanted to bring it up so that you would see like that's why this notation is usually introduced at some point, because it just allows you in a more like elegant way to say things that you were saying with dot dot dot. So like that sort of infinite sum, like this is in a sense what's called like an infinite sum roughly, and that's like a series, and that's like you'll do series a lot in Calc 2 if you ever end up taking it. Okay, so that's why I'm not don't want to spend a lot of time doing this, and this is like the only thing I'm going to say. Like I'm not going to ask you to solve anything specific with this sigma notation, but at least once if you take Calc 2 and you see the sigma notation, now you like at least you have like an idea of where it comes from. So it's just like a nice way to write sums. Is that making sense? I thought like I thought I had not made it. I did not publish it. I mean, you can complete it, but you also don't have to complete it. Let's leave it like that. I mean, it's good practice if you want to complete it, but yeah, I wouldn't. I don't want to ask anything about specific about that. So yeah. Um. I thought that I had not. I will check it whether I made it public. I thought I had not published it, but yeah. So right, like so as I was saying before making the quiz available. So my plan is over the weekend I'll try to send you some more practice problems for the final. And then I already did cover everything that I wanted to cover for the final. So what we can do on Monday, Tuesday, and Wednesday is kind of like try to do it more like interactive. So just come with any questions that you have on any topic of the course, because it's fine. The final is cumulative. So come with any questions can be from limits, mean value theorem, intermediate value theorem, whatever you want, and then we can just work on that. So it's more like extended office hours. Yeah, I'll send those. I'll send those over the weekend. Yeah, correct. Um, So, but I did wanted to finish like with some days in advance, because so that way you're not studying new material for the final, like the day before the final. So yeah, but I'll send you those review sheets. I'll try to get them done tomorrow or on Saturday. So I'll send you that as well. Okay. Let me just make the quiz available if in case. Oops. No, I cannot. Okay, yeah. Yeah, I'm trying to publish it. I don't know what Canvas. Okay, Canvas wasn't working too well. Okay, so now you should be able to take the quiz if you want, and then as usual, just upload the solutions once you're done. So yeah, but I'll send you all the material for the final sometime by the end of the week.